마지막 세션은 IBM 퀀텀 김보선 과장님께서 Chemistry Beyond Exact Solutions on a Quantum-Centric Supercomputer 라는 주제로 발표해 주시겠습니다. May I have your attention, please? We will now begin the fourth and the final session of today's industry session. In this session, Bo-sung Kim from IBM Quantum will give a presentation on the topic Chemistry Beyond Exact Solutions on a Quantum-Centric Supercomputer. Please welcome. 큰 박수 부탁드립니다.
Hello everyone. My name is Bo-sung Kim at IBM Quantum. I'm leading Korea technical enablement, like supporting your researches as well as like the quantum computer physically located in front of this place. It was supposed to be in like Korean presentation, so I will like English presentation, so I will speak in English. But you're free to like ask questions in Korean after this presentation ends. And actually, it is supposed to be like Ridashit will be here for this presentation, but like due to the flight schedule disruption, he could not make it today. So I'm covering this topic on behalf of him. So before we start, I'd like to advertise something like happening next week as well. There will be Yonsei IBM Road to Utility workshop happening in at the main campus, Sinchon campus at Yonsei University. We'll be also covering some basics of quantum computation as well as like error mitigations and Qiskit add-ons we launched last year. And we'll be also covering this sample-based quantum diagonalization deep dive with hands-on experience on next week. So Ritachu will be there, so you'll be able to see him and ask more questions and details about this SQD. So yes, it will be nice. Everyone, if you can join this workshop, we'll be able to see you again in this workshop. So let's start. We'll first start from the common belief about this quantum computer. Today what I will be talking about is about this sample-based quantum diagonalization, which was also mentioned in the previous presentation by Charles. He also mentioned that this SQD is one of the most state-of-the-art quantum algorithm that we have discovered and we are trying to apply to many different domains. But to introduce this SQD, we must start from this common belief of like how the quantum computers have been like misled to like general domains about its application. So here we mostly say that like pre-fault and quantum processor, of course it is in isolation, can attend realistic formulations of nature. For example, we may look into this FE4 and S4 cluster, which is normally, which is very like important sign of strong correlations in protein, in biological materials. So here to simulate its energy and eigenstate, it requires like 72 qubits in TCP-DKH basis set with 6.7 million Pauli operators, and it with requirement of 10 to the minus 10 precision on each operator for this achieving this chemical precision. Each circuit, now when we map this onto our previous like VQE circuits, each circuit must be executed 10 to the 20 times, and this runtime reaches like 3 million years, which is fairly unrealistic. But now what I want to claim on today's discussion, today's presentation, is that this classical the classical distributed computing, which we call normally supercomputing. Supercomputing enables quantum processors to address these complex problems with a few large quantum circuits, which means it can, like classical computers can accelerate these quantum algorithms and even support and achieve more behind the classical and quantum state-of-the-art application. So just for an overview, we will come back to this, or like we will look into each figures at the end of this presentation. But just for an overview of these results, you can see that we have simulated this N2 molecules, or like Fe2S2 cluster, as well as like Fe4S4. We have simulated its energy levels and energy bounds and its eigenstate with very comparable range within this, with the classical state-of-the-art algorithms. So how did we achieve this? Now we are going to how we did and the method we applied for this simulation. So now we want to look into this chemistry on a quantum-centric supercomputing. Now we will call this like QCSC, quantum-centric supercomputing, is the term we are thinking of a quantum computer that is supported by the classical supercomputer, which will enable us much like go further behind the just like classical computing or just quantum computing. So here we are applying the quantum estimator that uses this massive classical computing to process individual quantum samples. So now we have quantum computer in the center, and we have a lot of other classical workloads distributed over these classical computers, and this massive classical computing will supporting our quantum computer. And here we are also using this class of quantum circuits of tunable depths to make this accurate preparation of molecular ground states. So these two will be the point I want to make throughout this presentation. So we will look into how we have distributed workloads over these classical computers, and also how we made this tunable depth class of quantum circuits. So these two will make over our full SQD algorithm. So let's first look into this quantum estimator part. Quantum estimator, we call this whole protocol as sample-based quantum diagonalization, SQD. So we are using some samplers. If you are familiar with like this area, you may notice that previously we also used like estimator, which is focused on obtaining the expectation value from our experiments. But here now we are looking to our sampler, and so we have these samples, and now we are looking into these samples to get some signal of chemical reactions or chemical bondings or any other things. So this workflow looks like this. At first we will have this psi state, a state psi prepared in our quantum circuit with a very advanced encodings we want to apply, which will be explained in the later half of this presentation. And so once we have this circuit, now we are putting this in. Now we are getting the value or like configuration x tilde from the using the sampler. And then once we have these samples, now we are going to our classical supercomputers to do this configuration recovery. Now we have this samples of like here we say like 0, 1, 1, 0, 1, 1, 0, and some probabilities of those samples occurring. And then we will, what we are doing this year is subsampling from this sample, subsample some certain like k number of sets from this sample, and we orchestrate distributed computing. What to do is this one, eigenstate solver will be applied to each subsamples. So here we are like subsampling this whole whole sampled space, and using the like ordinary eigenstate solver, we'll be solving the Hamiltonian energy of each state, and then we'll collect the lowest energy and average occupancy, and then we will optimize this one in like self-covering, self-consistent loop. So we optimize this one like to recover or like retrieve the signal we want to see in this whole sample, and then now we iterate this whole cycle again and again for like certain number of time to retry the signal from the noisy devices or noisy simulation or noisy experiment, and then reach the outcome we want to get from this whole workflow. So let me quickly introduce the properties of the SQD estimator first. So here, we have four specific characteristics of the SQD here. First one is that we have no false positives for the ground states. This is the like intrinsic characteristic of this whole SQD workflow. Here the like energy estimate is always an upper bound, so we don't need to be like cautious or like worry about finding a false like ground state or like false ground state energy here. So that is one characteristic obtained from its theoretical property. And then second, we can also take the advantage of large-scale distributed classical computation. So here now we are sampling, like subsampling from the given configuration, and then using the classical computers or like classical resources to compute the ground state energy. We are now free to use like supercomputers, so-called supercomputers, to compute, like make this computation happen in a very small time. So this is the like second takeaway. And the third one is the complete mitigation of quantum noise, given enough running time, is like kind of assured here, while it is exponential in the noise rate. So in some sense, you can also like assume this SQD protocol is the method we are applying, some kind of like error mitigation technique we are applying to the samples in the experiment, like samples or like sampler experiment. So here it also like mitigates this like quantum noise while the configuration loop is like going over and over again, and this will like retrieve the signal in our sample, which means the quantum noise will be mitigated throughout this whole protocol. And the last one is that the performance is guaranteed for concentrated wave functions. So here, the performance is, of course, this performance depends on what kind of molecules or like what kind of system we are simulating. But here, this SQD is like, if you have more like questions about this, you can ask it after the talk. But here, there is a guarantee for certain concentrated wave functions. This will be work in certain. This SQD will approximate the ground state energy in a like certain degree of error bar. So these four are the key properties of SQD here. So now we applied or we run this whole SQD algorithm on our Torino machine here. Hero machine we have in our cloud. You can access through the cloud access as well. And using the Fugaku machine in Japan, which 6,400 nodes at 32 gigabytes or with 48 cores, which is the one of the most performative supercomputer over the world. And here, one of the key concept or key breakthrough we had to make was in typical applications, the data transfer between quantum and classical is normally it is limited to the circuit itself or the expectation values or circuit parameters. But here now we are looking into our sample, the data, the binary data we obtain from the quantum computer. So it now goes to enormous size. So here we are using the largest possible data transfer between quantum computer and classical computer, and we are sending this all bit strings input from the quantum device. So information, so this information transfer, data transfer between quantum computer and classical computer was very important, but still we make it. And then here now we having this all information about the samples. We are obtaining much better, accurate and noise resilient estimates through this. So skipping one slide and looking into its performance of noise resilience, we can see that at first, before we are applying this SQD, this noisy signal, we are looking to this N3 molecule, N3. And here, the noisy signal of this whole, this experiment was look like this, green or yellow line. While still it is still you can see there is certain signal that we may want to, sorry, this is the error bar. So you can see that the error exceeds 20% at certain noise level. But here, when we apply this technique, SQD techniques, you can see these signals are recovered in the even in the white noise level. You can see that this level error is less than 20%, and it even gets better, better at the lower noises. So this whole looking into this whole plot, you can see SQD actually making recovering all the signal from the experiment. So yes, this was the part about our algorithms, so classical, how we have classically distributed this whole workflow over classical resources. Now let's look into the quantum circuit we used. So quantum circuits for chemistry, we also proposed the local unitary cluster Jastrow ansatz, which is in short LUCJ. And if you look into the circuit, it looks like this. Now, one of the key problem or key something we had to overcome was that we have a hardware that has some restrictions in topologies and restrictions in connectivity, and we also had this but still we had to simulate this physical system, which use this physically motivated system. And now this LUCJ circuit lies between this hardware efficient circuit and physically motivated one. So here now we are having some physical motivations from derived from coupled cluster, those things you have been heard a lot about, like UCCSD or CCSD in the chemistry area. But still, this LUCJ circuit is not deploying the full UCCSD circuit in our quantum circuit, but now we're making it some more hardware friendly. So here, because IBM computers have this heavy hexagonal lattice, now we using this LUCJ circuit, this makes this device-specific connectivity, still obtaining a very nice results and minimizing the effect of noise. So looking deeper into this LUCJ ansatz, we first start from this unitary coupled cluster, singles and double. Here, we're looking into unitary coupled cluster, and single and double excitations are applied in this Hamiltonian. But here, we are not making this building this full Hamiltonian, but here we are applying this dividing or separating it like Jastrow. So here, if you look into the bottom figure, you can see that J, it is divided by alpha and beta orbitals. So the gates are applied only within alphas and betas first, and then apply this some interactions between this alpha and beta orbitals in this yellow block. So by doing this, we are making it more hardware efficient and still capturing the key configures or key features of the electron structure and the materials, the feature of the material. So, and then here we also, here you can see there, the orbital Hamiltonians are applied before and after these Jastrows. Still, you can see the detailed configurations, so detailed terms in these whole formulas. But now, yeah. So we are doing this, and as you can see, there are alpha and beta orbitals distributed over, and then now we are applying this Jastrow Hamiltonians with this certain number of single gates and 2 cubic gates, and then Jastrows between alpha and beta orbitals are applied over between this alpha and beta like this. But in this case, you can see that in A, we are doing this in every single alpha and beta orbitals, but which is the most ideal, but which is the same with the common unitary coupled cluster UCCSD. But what we are doing here is that although we can also reduce the number of Jastrows between this to only to capture the key features of the dynamics, reducing it to 2 Jastrow in bonds distance 2, or here at distance 4. But we can still make this whole ansatz simulating the circuit with certain degree of approximation. And at the last, we are applying this ansatz qubit to connect these different qubits. So by doing this, we are fitting this whole circuit into the hardware we have in real, which makes the best performance at the end of the day. So let's also look into the properties of this ansatz. First, here in AOCJ ansatz, parameters can be initialized from classical calculations, like for example, like CCSD, from the easier and faster simulations we can do. So yes, these parameters can be initialized and applied to our systems to get better approximation. And second, we can do this like numerical simulations for this small, for the smaller size problems. And it suggests that it can outperform some classical couple cluster in certain problems. So, which is quite promising for the larger circuits we are planning to execute on our quantum hardwares. And third one, the circuits are hard to simulate classically, which is also very important when we are looking to our quantum advantage. And thirdly, lastly, it maps directly onto our quantum hardware, which is we have intended over the time without the need for swap gates. So let's see the circuit in the lowest level. Still, this is not compiled or transpiled yet, but you can see that it is very implementable on your on your hands or on your laptop as well. So the workflow is the same as I introduced. So we start from certain initial state to say we can start from Hartree fork state for the first estimation, and then we apply the unitary evolution, unitary Hamiltonian revolution in some ordinary circuits. This is somehow optimized, so it is sparser than the last one. And then this is the important part where our Zostaro is applied. Here it is applied, you can see that in the left half of this circuit, it is almost similar to the UCCSD single and double excitations. Here single excitations or single and double excitations are all applied. And then while there is no zoom in into the later half of this Zostaro, you can see there is some connection between the upper half and the lower half is connected with some 2-qubit gates, which is the Zostaro I have mentioned earlier. And then if you look into the this right bottom corner, this is mapped onto this quantum qubits on our hardware. You can see this is the heavy hexagonal lattice you normally see in our IBM hardwares, and these are connected. This first qubit and the first qubit on the other side. You can see one is alpha and one is beta, and this is connected by one ancilla qubit between this cluster, which is applying this the Zostaro between alpha and beta. And it can be repeated, you can see it is 4 at distance 4. So here, every time after the 4 alpha and beta orbitals are computed, you can see this Zostaro between alpha and beta are executed again between these 2 clusters. So this whole workflow is applied on our hardware like this. So for example, if you look into the, let's look into the smallest one, our FE2 and FE2 S2 cluster. You can see that there is an alpha cluster mapped onto our hardware and beta cluster on the other side, which is connected by 5 ancilla qubits applied to make this entanglement between these spin spaces. So this is the the idea we wanted to implement on our AOCJ circuits, which is hardware efficient, still physically motivated, and capturing the key features of our system. So lastly, let's look into this theoretical performance of AOCJ and SKD. So this is theoretical one. This is simulated with our fast simulation of ferromagnetic quantum circuits, FFSIM, in our Qiskit community. So this is the simulation, not the actual running. But here you can see that our AOCJ circuit is going very closely to the exact solution in this N2 molecule with 631G basis set. We also listed the other results, experimental results from like RHF and CISD, like CCSD as well. You can see that normally this like CCSD is the fastest or like most efficient protocol you can apply to this problem, but still you can see in qualitatively in CCSD you can see there is some like drop after this like bonding length. The energy level goes down again after like around like 1.8 Armstrong. You can see it is like dropping, but in our AOCJ circuit, it is like intrinsically ensuring this circuit will be simulating the upper bound of the energy, and you can see it is thus capturing this behavior of this exact solution, which is great, and something that we can say on evidence of it outperforming the classical simulation. So yes, that was the simulation we have performed, but let's look into our actual hardware and experiments. So it's the same one, but now we are having this data from our actual quantum hardware, Heron. And here we are also presenting this like HCI simulation, which is also very like, which is one of the like kind of competitor we set for our simulation or like for our experiment. You can still see that this quantum solution is almost like not really going very bad, and it is almost on the line or on some area that makes some scientific discovery. So it is almost like undistinguishable between like other classical methods we have presented, and even like you can say that this quantum simulation is capturing the like exact solution very well, or even better than others. Still, it is like and it is at like 58 qubits, which is very like large, fairly large compared to the like previous simulations. And this breaking of the like N2 bond here is like test of the accuracy for this this performance of like simulating the electronic structure. But you can see that this quantum data itself also like qualitatively like capture the multi-reference ground state on molecular system of 52 spin orbitals. And then now we can move forward to some more like practical simulation. So this one like Fe and like the iron sulfur cluster, which is the sign of the strong bondings in our biochemistry. You can see that here we are also comparing it with our other like CCSD and the HCI as well, and DMRG, which is the best like state-of-the-art simulation obtains. And now we are looking into the energy variance and the ground state energy. And here, what we had to see is like two key features of this plot. Is that what we want to see first is that this data should lie on a single straight line, and you can see it does. So you can see our data does make this certain line or straight line towards some value. You can like extrapolate the value at the like zero variance, and which is like fairly well simulated or like experimented with our device. So in like eigenstate A and eigenstate B, it almost reached the precision of we are obtaining by this HCI method. Not as much as the MRG, but A and B, you can see it is almost like performing as well as like HCI does in this example. And then in eigenstate C, you can see it is almost like reaching the precision of the MRG, the density matrix renormalization group method is making. So you can even see that in real experiments, we also see, or like we can make this whole experiments really in our quantum device. And lastly, like pushing to the extreme hardware capabilities, we also make the simulation of FE4S4, which requires like 77 qubits and like 3,600 like 2-qubit gates. The largest circuit for like molecular simulations have ever executed in the like whole world. So this is like pre-fault-tolerant quantum data, but it also like retrieves this signal. It does not like I'm not saying it is like outperforming the classical method at this scale, but still you can see the potential of it can be improved. Here the quantum data. Here the quantum data is reaching the accuracy of CISD or like some HCI fits, and this we can say that quantum computer can be a method of scientific discovery or research in this scale, even in this scale, supported by the classical supercomputer. So at the end of the day, the like more classical compute like extracts better signals from noisy quantum data. And in summary, so I'm pointing out these four. So first, quantum-centric supercomputing could enable realistic applications in pre-fault-tolerant quantum processors, which is great, and which is something different from our like previous assumptions or like common bits. And then second, the SQD algorithm executes a few large quantum circuits using like large-scale distributed quantum classical computing. So this one is how we made this whole experiment work using both quantum computer and classical resources we have. And third, we simulated molecules beyond the reach of exact classical solutions. Actually, the FE4S4 simulation, it is the beyond the reach of exact classical solution, where some like only this like approximations or experiments or the method to find the ground state energy. Here we apply 77 qubits and 3,500 2-qubit gates with a detectable quantum signal. We could see there is a like linear extrapolation possible with our signal, which can be like improved by increased classical processing. And lastly, the chemistry is just one potential application of quantum-centric supercomputing. So you can see that there is some potential of applying this whole protocol to every different areas. And this is why we are looking forward to seeing applications in other domains. So that's the end of my slides. And thank you for listening. And I'm free to answer any questions you might have. 질문 있으시면 한글로 해주셔도 괜찮습니다.
네, 발표 잘 들었습니다. 감사합니다. 제가 궁금한 게 시뮬레이션 결과로 이제 N2랑 F2, S2랑 FE4, S4 분자들에 대해서 이제 시뮬레이션한 결과들을 보여주셨는데 혹시 이 세 개의 분자가 케미컬 시뮬레이션이라는 넓은 분야에서 어느 정도로 representative 파워가 있는지가 궁금하고 혹시 그리고 뭐냐 지금 이 SQD 알고리즘이 기존의 다른 알고리즘들 DFT나 DMRG 같은 알고리즘들에 비해서 어떤 영역에서 더 우위를 가지고 있는지에 대해서 저희가 아는 바가 있는가가 궁금합니다.
네, 좋은 질문 감사드립니다. 첫 번째 질문하셨던 거는 이제 시뮬레이션 했던 이 N2나 아니면 FE2, S2 아니면 FE4, S4 클러스터가 어떤 의미가 있는지를 질문해 주셨는데 사실 저도 케미스트리나 아니면 바이올로지 쪽 전공은 아니기 때문에 그거에 대해서 정확하게 답은 드릴 수 없다는 점은 양해를 해주시되 제가 이제 찾아본 바에 따르면 이제 N2나 아니면 이제 특히 FE2, S2나 FE4, S4 클러스터가 아까 발표 중에 말씀드린 대로 어떤 저희 단백질 사이의 결합 그리고 그 중에서 약간 강한 결합이 있을 경우에 이 FE2, S2 클러스터나 FE4, S4 클러스터가 이제 있는 것을 발견한다면 그것이 이제 강한 결합이 있다라고 생각을 할 수가 있고 그리고 이거를 이제 그래서 따라서 이걸 시뮬레이션 하는 것이 어떤 뭔가 단백질 간의 결합이 어떻게 얼마나 강하게 이루어질 수 있는지 이런 것들을 시뮬레이션 하는데 활용될 수 있는 걸로만 이해하고 있습니다. 혹시라도 이제 더 뭔가 이 분야의 전문가분들이 계시다면 더 자세한 설명을 드릴 수 있을 것 같은데 일단 저는 그 분야에 대해서는 잘은 몰라서 이 정도로만 설명드리는 것을 양해해 주시면 감사하겠습니다. 그다음에 두 번째 질문 주셨던 내용이 혹시 두 번째 질문 주셨던 내용이 뭐인지 한 번만 말씀해 주실 수 있을까요? 네.
SQD 알고리즘이 기존의 DFT나 DMRG 같은 머티리얼 시뮬레이션
네.
알고리즘들에 비해서 어떤 분야에서 우위를 가지고 있는지.
네. 일단 보통 이제 지금 이제 DMRG 시뮬레이션 같은 경우에는 저희가 직접 하지 않고 논문을 보시면은 이제 다른 연구에서 이제 DMRG 시뮬레이션 한 데이터를 이렇게 가져와 가지고 저희가 레퍼런스로 삼았는데 그만큼 이제 DMRG 시뮬레이션은 코스트가 굉장히 많이 들고 그 다음에 비용이 굉장히 많이 드는 대신 이제 좀 더 정확한 시뮬레이션을 할 수 있는 에리어에 있다고 보시면 되고. 대신 이제 결과를 보셨을 때 CCSD 같은 메소드나 아니면 HCI 메소드랑 저희가 주로 많이 비교를 했었는데 이쪽에서는 조금 더 이제 효율적이고 빠른 시뮬레이션이 가능한 대신 어느 정도 약간 아까 CCSD가 뭔가 N2 본드에서 제대로 이제 그라운드 스테이트 에너지 커브를 제대로 시뮬레이션 못한 거랑 비슷하게 약간 에러가 있을 수 있는 거 어프록시메이션이기 때문에 일정량의 에러가 있을 수 있다는 점이 이제 약간 문제가 될 수 있고 그에 반해서 이제 SQD 같은 경우에는 물론 정확하게 모든 다이고널리제이션을 다 수행하는 건 아니지만 어느 정도 어프록시메이션은 하되 대신 이제 이것이 양자 시스템을 시뮬레이션하는 이제 방법이라는 것, 양자 시스템에 대한 시뮬레이션이라는 걸 잘 살려서 조금 더 정확한 시뮬레이션을 할 수 있다. 그리고 여전히 빠른 시간 안에 시뮬레이션이 가능하다. 이 두 가지가 이제 메인 테이크어웨이가 될 수 있다고 생각합니다. 좋은 질문 감사드립니다.
안녕하십니까. 우선 강연 감사합니다. 잘 들었습니다. 제가 2학년 학부생이라 잘 이해한 건지 모르겠지만 궁금한 점이 있어서 질문드립니다. 혹시나 잘못된 내용이면은 알려주시면 감사하겠습니다. 마지막에 이 기술을 매니바디 피직스에 가능한 고유 상태 계산 이외에 다른 다양한 분야에도 사용할 수 있을 거라고 기대한다고 하셨는데 LUCJ 계산 과정에서 모든 오비탈에 대해서 회로 계산을 하는 것은 클래식 커플드 클러스터와 같지만 LUCJ 계산 상태에서는 그 필요한 특성들만 가지고 계산을 하기 때문에 속도와 정확성에서 차이가 있다고 설명해 주셨다고 이해를 했는데 이 필요한 특성이라는 게 그 외부에서 직접 지정을 해줘야 되는 건지 아니면 회로 계산 과정에서 자기가 직접 알아내는 건지 궁금합니다.
어떻게 이해를 하시면 되냐면 모든 알파, 베타, 오비탈 사이에서의 인터랙션을 시뮬레이션 할 수 있다면 당연히 이제 가장 좋기는 하겠지만 지금 여기서는 이제 저희가 가지고 있는 양자 컴퓨터의 그 구조상 모든 그 알파, 베타, 오비탈이 인터랙션을 하는 것은 지금 이제 헤빅사고날 레티스라고 하는 이 구조에서는 그 굉장히 비효율적이거든요. 그래서 그거를 전부 다 시뮬레이션 하는 대신에 이제 그 오비탈 4개마다 한 번씩 이제 인터랙션을 가함으로써 이것이 하드웨어에서 바로 시뮬레이션이 가능하도록 이걸 약간 변형을 했고, 그다음 이제 논문을 보시면 거기서 이제 이게 4번마다 적용되는 거랑 그다음 한 번마다 적용되는 거랑 어큐레시가 어느 정도 차이가 나는지가 나와 있습니다. 근데 실제로 보시면 거의 이제 큰 차이가 없고, 그리고 실제로 아까 데이터를 보셔서 아시겠지만 이제 데이터에서도 이게 실제 어떤 그라운드 스테이트 에너지를 계산하고 어떤 그라운드 스테이트를 계산하는데 별 이제 문제가 없는 것을 확인을 할 수가 있습니다. 그래서 이런 어떤 약간 포기할 수 있는 것들을 포기함으로써 어프록시메이션이 어느 정도 들어감으로써 이제 더 빠르고 더 정확한 시뮬레이션을 가능하게 하는 것이 이제 이 그 LUCJ 안사치라고 보시면 될 것 같습니다. 좋은 질문 감사드립니다. 네, 다른 질문 또 없으시면은 여기서 마무리하도록 하고, 혹시라도 더 궁금하신 점 있으시면은 직접 와서 또 더 물어봐 주셔도 괜찮으니까 네, 편하게 또 질문 또 주시면 감사하겠습니다. 수고 많으셨습니다.